Alkenes. Alkenes have a general formula of CnH2n. They are unsaturated compounds, meaning they have a double bond in them. As you can see here, ethene, which has a double bond, and is completely saturated with hydrogen. This classifies for any alkene or any cycloalkene. Molecular orbitals. So the bonding in alkenes is a bit different to alkanes, given that they have a double bond. So effectively, they have single sigma bonds from the overlap of two s orbitals, as you can see, which will be represented as the 1 line. Here is the overlap of the two orbitals, and then you have double pi bonds formed by overlap of the other bonds, which form a double bond over here, across and below the axis. And that can be represented in many different ways. So if this is a badly drawn model, you see here is the sigma bond, and here are the two pi bonds. Alkenes exhibit structural isomerism, meaning that they have compounds with the same molecular formula but different structural formula. Effectively, this means different bonds. So one alkene molecule can have many different isomers with different bonds. They also exhibit geometric isomerism. This is a type of stereoisomerism. This means they have the same molecular formula but different 3D orientations of the atoms in space. So they have cis-trans isomerism. So cis means the same side. Think of it like cis sisters. They're on the same side. Whereas trans means they'll be on different sides. To exhibit this, an alkene will need no free rotation around the CC double bond, which is caused by the double bond here. And they need two different groups. This won't work for, say, ethene, because all four groups be the same, as if this was a hydrogen and this was a hydrogen. However, you have two different groups on each end of the double bond. Therefore, it can exhibit this. They have different physical properties, but will have similar chemical properties. So now moving on to the chemical reactions of the alkenes. They go through reduction/addition reactions. This needs 150 degrees Celsius and a nickel catalyst or any inert catalyst, but usually nickel's the best one. It's also hydrogenation, and it's reduction as there's the gaining of electrons, and also classifies an addition reaction because two reactants become one. So then you get ethene and hydrogen, and those react and form an alkane. Note this is used for food manufacturing of margarine by catalytic hydrogenation of unsaturated vegetable oils, which is named in the spec. They also go through electrophilic addition reactions. So an electrophile is an electron-deficient species with a vacant orbital. It's often, but not always, positively charged, but it will be attracted to electron-rich sectors. This is also an addition reaction because one or more groups is added to give a single product, and it's heterolytic bond fission, as it results in producing two hetero products. So, as if you were going to add this, two different products. So the first one will be with halogens. So we're just going to quickly draw this out. Apologies for the bad drawing. So with a halogen, they will form a dihalogenoalkane. So we'll take a simple molecule such as ethene, and we'll react it with halogen, say, let's go for bromine. So what happens is we get a dipole on these molecules here. So that's covered in intermolecular forces. To begin the reaction, an electron pair moves from the double bond into this delta positive bromine. And then this effectively means this bond here is popped out, and these electrons move to this delta negative bromine. And this forms an alkane. And this is because the bromine molecules are able to attach to here as excuse me, this carbocation has a positive charge, meaning that this now fully negative bromine ion, as opposed to here with its lone pair, is able to go up there, which means we form a dihalogenoalkane known as bromoethane. So they also undergo electrophilic addition reactions with the hydrogen halides, which forms only a halogenoalkane, not a dihalogenoalkane. Let's get the pen out. There we go. So again, I'm just going to use simply ethene. It's a good way to show what goes on in the reaction. And it's quite similar. However, you have to remember there's no dark here. And we're also using a halide, not just that, the hydrogen halide, not just the halogen. So we'll stick with bromine, and we'll have it react with hydrogen bromide. So in this case, these are the dipoles, and once again the electrons move onto the hydrogen as opposed to the delta positive bromine from last time, and once again this bond here will be popped and move on to this bromine, and this once again needs to form an alkane, but this time instead of a bromine here we'll add a hydrogen, because again hydrogen. So here again we'll have another positive charge and a bromine ion, full electric charge, negative charge, double bond, no, lone pair, and this arrow moves the electron pair into the carbocation. Forming our product. One bromo ethane. Remember, one only, as opposed to the di. In addition, alkenes react with steam in the presence of an acid catalyst, and an alkene plus an acid plus steam will form an alkyl group in that it will become an OH functional group. So it'll also react with potassium manganate, and this will only happen in acidic conditions or with NaOH2 in some cases. It is the oxidation of the double bond. So this is an oxidation reaction, and it produces a diol, so 2 OH groups. And the purple solution will move from purple to decolorized. So potassium manganate acts as the oxidizing agent in this reaction here. And as you can see, we have di 2 OH groups. So they also can form polymers by addition polymerization. So here we have a monomer of ethene. Remember this N here, because you have to represent the fact that it's a number of molecules. And what we can form is polyethene, a polymer of this monomer. And remember, the key thing here is to always get rid of the double bond, because you're adding across the double bond. And obviously, because it's N, it can be whatever units it is. So say if there was 6 units here, then this would carry on six times, if that makes sense. So it would carry on 6 times, and that would be 1 unit, that would be 2 units, 3, 4, and so on. So polymer disposal is another thing that's mentioned on the spec, and it mentions specifically that waste polymers can be separated into specific types of polymer for recycling, incineration to release energy, used as feedstock for cracking, which I'll go on to in a second. And it also mentions how chemists can reduce the problems caused by polymer disposal by developing biodegradable polymers and removing toxic waste gases caused by incineration of plastics. So the test for alkenes is the same as their functional group, so it's a test for the CC double bond. You add either bromine or bromine water, and it will colour change from orange to colourless if it's a positive result. So here we have a negative test, and here we have a positive test. So an alkene is present in this one. So this is often used in practicals, and it's a good way to test between an alkane, which will have that, as opposed to the double bond and the pi bond system in an alkene. Finally, we go on to cracking. So cracking is the process of long hydrocarbon chains of alkanes, which are cracked to form short chain alkanes and alkenes. So a longer chain alkane can be broken down into a shorter chain alkene and a short chain alkane too. Just to mention, this would be heated up. You have your mineral wool soaked in paraffin, and then this porcelain chips here, or this could be easily be aluminium oxide or a catalyst here. And then you follow this along here, and the gas moves down